Okay, hello. This is a intro to sequences lesson. Okay, what is a sequence? A sequence is just a series of pictures or numbers that have a pattern. So how do we find terms in sequences is really our essential question for this. So you can see in this picture below, we have three pictures, and you'll notice that the pictures are rotating. In this case, they're rotating clockwise, and clockwise 90 degrees. So if I look at each picture, the last one is here. If I want to draw the next one, I'm going to maybe start with the triangle and use that as sort of my base. So this is in, looks like the upper left. So I'm going to draw a triangle down here. I'm sorry, upper right. And then put this one in the lower right. And then the dot moves to this space, and the X right here. So I want to find the next term in the sequence. It would be this. And that's all sequences are. And we're going to use our skills to find the next terms in different variety of sequences. So what is a sequence? Well, the definition of a sequence is this. It's a set of pictures or numbers with a pattern. That's it. Each picture or number is called a term. Okay, so in this previous one, each one of these, that's a term, that's a term, and that's a term. And then this is the next term after that. Okay, we have a couple of different types of sequences. We have finite sequences. And a finite sequence, finite means just that it ends. Okay, so it stops somewhere. So a finite sequence would be a sequence with a limited number of terms. An example would just be like 1, 2, 3, 4, 5. It starts at 1, it stops at 5, and it's done. So it has an ending spot. An infinite sequence, though, is a sequence that does not stop. It's unending. So unlimited number of terms or unending. An example of this would be the set of whole numbers. This right here is the set of whole numbers. So 0, 1, 2, 3, 4, 5, all the way up to infinity just keeps going. So it never ends. And you'll notice to indicate that they'll put those three dots at the end to indicate that this continues to go. That's not here in this case. Okay. The most famous sequence is called the Fibonacci sequence. In 1202, Italian mathematician Leonardo Fibonacci described how fast rabbits breed under ideal circumstances. He noted the number of pairs of rabbits each month, and then this formed the famous pattern called the Fibonacci sequence. And here is the Fibonacci sequence. It's 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. And you might say, well, what is the pattern? The pattern here is if you want to find the next term, so let's say you were just given this. If I want to know the next term, what you do is you add the two previous terms. So let's say I want to know what comes after 2. Well, I take 1 plus 2, and that's my next term. Okay? And then to get this term, I go add these two. 2 plus 3 is 5. Then 3 plus 5 is 8. So you're just adding the two previous terms, and that gives you the next term, called the Fibonacci sequence. This is a pretty cool sequence because, well, here's a picture. If you write a square with a side length of 1, there it is, right here in the middle. There's 1. And then here's another one. We're just following the terms in the Fibonacci sequence. And then the next one is 2. Put it here. And then 3, and 5 and 8 and 13, and you can see the different pictures there. Now, if you connect the corners of each square, so let me see if on this one, oops, it might be, you just take this and you connect the corners like that. Right? Now, I just do them straight. But now if you start to do that with a slight bit of curve, then you get a spiral. And this spiral is pretty cool because this is called the golden spiral. And it's, again, created by drawing circular arcs that are connecting the opposite corners. And the reason that this is pretty cool is because this shows up in nature all around us, and that's why the Fibonacci sequence is so famous. So here, there's the spiral again. You'll notice here's this picture is an aloe, which is really cool. You can see the spiral in there. This curl occurs at lots of different places in nature, but here are some examples. In a pineapple, in a pine cone, and it really is around us a lot. In a sunflower, you'll see it. Okay, some notation for sequences. Now, typically, when we do tables, we'll see like an X and a Y. So X is 1, 2, 3, 4, and Y, the output is 3, 7, 11, 15. This is a little bit different than sequence notation does N for the term number. Which term are we talking about? N stands for term number. And then A sub N, that's how that's written. I wrote that. You'll notice here, I said A sub N is written as that. When you see that subscript, that's how we say it. So this right here, I would say is A sub 1, A sub 4, A sub 7. So what that means is, what is the value of a specific term? So if I say A sub 11, I want to know what is the value of A sub 11. In other words, what is the 11th term? Now, I don't see that here, okay, because I don't have 11. It only goes up to 4. So I would have to figure that out, okay? But I do, on the bottom here, it says, what about A sub 1, A sub 4, etc., A sub 7? Let's do that. A sub 1, this is the term. You see the term would be that one right there. So A sub 1 would be this term right here, 3. A sub 4, we also know. Here's 4. Oops. 4. So A sub 4 is 15. Okay, now we don't know what A sub 7 is, but we could figure it out because it looks like there is a pattern. So if I write this out, it looks like in this sequence right here, as I go from left to right, every time I'm adding 4. 3 plus 4 is 7, plus 4 is 11, plus 4 is 15. So if I add 4 again, A sub 5 should be 19. A sub 6, add 4 again, 23. So that would mean A sub 7 should be 27. So even though it's not given to me, I can figure it out pretty quickly. Okay. So that's term notation and how it works. It's a little different than what you're familiar with, but once you practice it a little bit, it gets pretty easy. Okay, a recursive formula. There are two types of formulas that we'll talk about: recursive formulas and explicit formulas. The first is a recursive formula. And the recursive formula, they really use previous terms to generate the next term. So it might be one previous term or more than that. But really the key thing is here we're using previous terms to generate the next term. Okay, so let's try this. Maybe switch colors here. It says find the first 5 terms of the sequence. So I'm going to go over here and just write A sub 1, A sub 2, A sub 3, A sub 4, and A sub 5. So I need to know these 5 terms. Now, they do tell us the first one already. So that's done. Cool. So now I just really need to know the other ones. Okay. So let's do this. We know, here's my rule. This is the rule. And you'll notice over here it says for n greater than or equal to 2. So that means if you're going to plug something in for n, it has to be 2 or bigger. Well, the reason for that is because they already give you a 1. So then this rule only works if it's anything 2 or bigger for n. That's why they say that. Okay. So let's see if we can do this. We need a sub 2 anyways. So I'm just going to put a 2 in for n. So now here, I'm going to do that same thing. A sub 2 minus 1. And then, notice, remember, this is a subscript. It's written a little lower. Okay. And then plus 9 we'll do after that. Now, 2 minus 1 is 1. Okay, so really what I have here is a sub 1 plus 9. Okay, so that's how you find this. So this really up here where it says a sub n minus 1, it's really just a fancy way of saying this is the term right before this one, or the previous term. So you'll notice that this is the one right before this one. So the previous term. So this is really just a fancy way of saying take the previous term and add 9. So in my previous term to 2, here let's erase this, to 2 is 1. And I know what 1 is, it's 14. So a sub 2 is 14 plus 9. Okay. So that means this has to be 23. Okay. Now, if I want to do the next one, which would be a sub 3, right? I would want now to put a 3 here as well. So 3 minus 1 would be a sub 2. And then plus 9. So again, this is always going to be 1 before this because it says minus 1 there. So that always will mean the previous term. So take the previous term, which we already know that it's 23. A sub 2 is 23. So 23 plus 9. So all this sequence is saying is take the previous term and add 9. And so this is going to give me 32. So then I'll go write that over here. This is 32. So now I could write it out every single time for this next one and plug in a sub 4 if you want. But I know that I'm just going to be taking the previous term and adding 9. Well, my previous term now is 32. I'm going to add 9 to that. 41. Now take that term and add 9 again, and that's 50. So this recursive formula simply says take the previous term, add 9. And then here is my answer for the first 5 terms. So that's really all it is. You just have to get used to the notation. Okay, so let's take one that's a little bit maybe more challenging than that one. I am going to, let's do the same thing we did last time. Just write these out here. Okay, so again, I know this is recursive. The first term is 11, so I wrote that over here already. Okay, and then this, again, is the previous term. But this time, I'm taking the previous term, and you'll notice there's a 3 in front of it. That means I'm multiplying by 3 first, whatever that term is. And then after I multiply, then I'm going to add 7 to it. So we'll plug in a sub 2 and see how we do. So I'm going to plug in a sub 2. Maybe zoom in here a little bit. A sub 2 equals 3 times, I'll put that in there. Now I'm putting a 2 in for n. So that's going to be 2 minus 1. So I'm just going to write a sub 1 and then plus 7. So really what this is saying is take a sub 1, multiply it by 3, and then once you do that, then add 7. Remember, you got to follow order of operations. Well, I do know that a sub 1 is 11. So I'm going to go 3 times 11 and then add 7. Remember, order of operations says I got to do this first. So that's 33 plus 7. Okay, so a sub 2 is 40. Okay. All right. Now, what about a sub 3? Again, you can do this same thing. I'm going to take 3 times the previous term. So now remember, I'm putting a 3 in here for the third term, right? Our term number is 3 this time. Okay, so I'm going to put a 3 in there. That's going to give me 3 minus 1, which would be a sub 2. 1 before this one, right? Okay, and then plus 7. Okay. So 3. Now I know the previous term, a sub 2, is 40. Okay. 3 times 40 is 120 plus 7. So I get 127. Okay, now I need a couple more. So a sub 4. Now you can keep doing this, but you know that each time, what are you going to do? You're going to take the previous term, right here, previous term, and multiply by 3. Right? So I'm going to go 3 times 127. I'm going to add 7. Okay. So now maybe it's helpful to do that on your calculator. You might not know that in your head, so I'm going to pull up my MCA calculator. Okay, we'll try a different calculator. That one's not working. So I'm going to go 3 times 127. You got that, and then you can go ahead and add 7 if you want after that. So we get 388. Okay, now I need to do that again. So a sub 5, I have to take the previous term. So in this case, that would be 388 and add 7. So 3 times 300 times 3 plus 7, 1,171. Okay. So now we found the first 5 terms. Now a little bit more challenging than the previous one, but still doable. And then once you know the pattern, it's pretty easy. Okay, now occasionally they'll do weird stuff. And you'll notice here, this looks a lot different, okay, than some of the other stuff that we've been talking about. And in this one, it starts at N3. Well, I do have the first 2 terms that they gave me already, so that's kind of nice. So let's write it out. I got 3 for the first term. The second term is 4. The third term, fourth term, and fifth term I need to find. Okay, so again, all this is really saying is, it says a sub n minus 1. That means the term before this one. Then a sub n minus 2 means the term before this one, right? So really, this is just the previous 2 terms, okay? You'll see what I mean. Let's say we put in 3. Then this would be 3 minus 1, and this would be 3 minus 2. So if I want to find the third term, I'm going to take the second term times the first term, the previous 2 terms before this one. That's all that means. So I know those, luckily, and I know that a sub 2 is 4, and a sub 1 is 3. So this is 12. Cool. Now, if I want to know a sub 4, I just take the 2 terms before that, which is these 2, and multiply them. So to get a sub 4, I'm just going to go 12 times 4. Okay, so that's 48. Okay, cool. Now, if I want to know a sub 5, I just need to take a sub 4 and a sub 3 and multiply them. So 48 times 12, which, let's just type that in, 48 times 12, 576. So again, pretty easy to use once you just understand that pattern and how it works. The notation gets a little weird sometimes. Okay, explicit formulas are a little bit easier. You can just go right to the term that you want. Explicit formula is a rule that defines the nth term of a sequence as a function of n. So you just put a 1 in, a 2 in, a 3 in, a 4 in, a 5 in, whatever term you want in for n, and it'll tell you what it is. You don't need previous terms. So we need to still find the first 5 for this. So I'm going to write that over here. The pen I have is not very fancy, so sometimes it looks a little weird. But I'm going to do that. If I want a sub 1, all I'm going to do is 7 times 1 minus 3. Well, I'm putting a 1. Notice, right? N is 1. That's why I put that 1 there. 1 minus 3 is negative 2. Okay, so this is negative 14. Okay, so now if I do 2, I'm just doing 7 times 2 minus 3. And that's negative 1. That's going to give me negative 7. Okay, now I'm going to put a 3 in. Well, that's 0. 7 times 0, 0. Okay, a sub, I suppose maybe I'll switch color like I have been doing. I'm going to put a 4 in for n, so that would be 7 times 4 minus 3. 4 minus 3 is 1. 7 times 1 is 7, right? I guess I should write that out, right? And then the last one would be a sub 5. And that one would be 5 minus 3, which is 2. So 7 times 2, 14. So you can see you just plug it in. Now if I wanted 100, I'd just put 100 in here and go. I don't need to know the 99th term. So explicit formulas are a little easier to use. Okay. Here's a different way that you might see an explicit formula written. Notice it's a lot different, but it still works the same. And isn't that bad. Oops, not 5, 4. There we go, and then 5. Okay. All right, now according to this one, it's a power, right? So I have to go, let's see, a sub 1 equals negative 2 to the 1 minus 1 power. A sub 1 is negative 2 to the 0 power. anything to the 0 power, if you type it into your calculator, is 1. Let's go ahead and do that. -2 to the 0 power. Notice we get 1. Okay, so the next one I need to put a 2 in for, okay? So if I put a 2 in there, 2 minus 1 is 1, so I'm going to get that. Now -2 to the first power is -2. Okay, a sub 3 is going to be -2 to the 3 minus 1 power, which would be 2. Now -2 to the second power, again, you got to make sure you put this in parentheses. -2 to the second power is +4. If you forget the parentheses, you're going to get -4. That's going to be wrong. Okay, so then a sub 4 is going to be -2. Put a 4 up in there. 4 minus 1 is 3. So -2 to the third power. -2 times -2 times -2, right? That's what that means. So that should be -8. Notice that one is negative. And then -2 to the fourth power. So this would be 16. Notice it goes positive, negative, positive, negative, positive. So this is one that changes back and forth. So that is sequences. One last thing is, how do you know if it's a recursive or explicit formula? An explicit formula, you're not going to see anything about previous terms. Notice this is an explicit formula just because it doesn't say anything about n-1, a sub n-1, or a sub n-2, or any other previous term. So that's kind of how you know. If you see one of these, or an n-2, or something like that, you know those are previous terms, and that's how you tell. So this has to be recursive. It also often will put this in here, but this is recursive. Okay, and that's how you tell. I hope this makes sense. Have a good one. Bye.